So this and the line joining the center and the, so if you have, so let's look at to normally you have this orbit, okay? Guys, pay attention. Right? Now this is the perigee direction. What is perigee direction? Perigee is this point. This point is perigee or periaxis, right? Perigee direction is the line joining the foci and the perigee, and just it goes on. Okay. Now your satellite could be here, here. So these are different positions of the satellite. It's orbiting. Got it? This is R1, or it is R at time t1. That's how you represent. Okay. Theta is, this is theta 1. That is a true now.
So do you always start off with the initial position though? So would that be the initial position at?
Not necessarily. This could be the initial position.
Oh.
There is no initial position as such. Okay. The initial position is when the satellite the launch vehicle releases. It goes up and it releases. So this is theta 1, this is theta 2. That is those are the true anomalies. So when the satellite is here at the perigee, what is theta? 0. And that's what we did here. Okay? Your RP is given to be 7,000 kilometers. So distance is from the, now you have to keep in mind, this is called the perigee radius. If you are given perigee altitude, what is the difference between perigee altitude and perigee radius? Altitude is? What is perigee altitude? If I give you the perigee altitude, what are you going to do? What is perigee altitude and perigee radius? Or perigee? Difference between those two? Perigee altitude is from the surface of Earth. Perigee itself is from the core of the center. So what is perigee? What is the relationship between perigee altitude and perigee radius?
It's the radius of the Earth.
Right. So perigee altitude plus the radius of Earth is equal to perigee, or the perigee radius. Got it? Make sense? So this includes the radius of Earth. Okay? So you get the true anomaly concept? Everybody? So if I say this is h square h is to mu, you can calculate what is mu? Gravitational parameter for Earth. Okay. So this is given to be, let's say this is given to be Earth. So you have to, this mu will be given to you. Okay. From that you calculate h. H you get as now what do you know about this h?
Is a constant.
It's the constant. So regardless of where this h is, the h is constant here, h is constant here. That is what you need to know. Okay. So now if I write RP1, what is RP1? RP1 is?
H squared over mu.
Right. So it will be the same h. Okay. So it is again h square over mu. I will not change h1, h2. I won't do that. You understand why? Because it's the same orbit. It's the same orbiting body. It will still be h square over mu 1 over 1 plus. Again, E is also equal to
1.
1. It's the same orbit. Got it? And cosine
1.
theta 1. So this is not, this is theta 1. You agree?
But I'll be theta 2.
This, so this was theta, this theta.
Oh,
This
Oh,
is,
yeah.
this is theta 2. Okay?
Very awesome.
yeah.
And delta theta is what?
H is
Theta 2 minus theta 1.
4, 1.
Yes,
Is that 74,000 or 741?
74,700.
Oh,
So you have, this is equal to 8,000 is equal to 74,700 divided by 1 over 1 plus cosine theta 1. This is 16,000. One over one. Okay.
But we don't know thetas, right? Theta 1 and 2.
Right. So you see here we can calculate theta 1, right? That's the only unknown. And here you can calculate theta 1 because that is the only unknown. So here you see theta 1 is, from this you can see that theta 1 is 41.41 degree. Is 96. It's degrees, it's not radians. Now what is delta theta? It is 97.18
18 minus 41.
And what is the relationship between P? Your goal is to find B. So you can say, you remember the relationship between in a triangle? So this is not necessarily right angle triangle, right?
Can you use the law of cosine?
Law of cosine, yes. That is what you need to use. So the law of cosine, you say B square is equal to
Could you also use the law of sines?
yes, you can use law of sines or cosines. Either one. From this, you get D is equal to 13 over
Where are you getting this? What is it? Is that? Okay, what is?
So this is the law of cosine. So if you have
Oh.
this as, so here it is theta. Okay? So you have a square plus b square minus 2 ab cosine theta. That's what it is. You can use the sine. Okay. Now can you do something like this in your midterm with the formula sheet? Now what you have to recognize is what formula to use and why this is 0. If you do that, then you can flow through the rest of the calculation. If you look at hyperbolic orbits, can I erase this part? Was the concept of escape velocity clear to you guys? Yes.
Yeah, isn't it 74,700 supposed to be squared? Is it 8 squared?
Square. Okay.
So you're ready to come in the back door.
So if you have, see, if you're looking at a hyperbolic orbit, you're right. It is square. Okay? That is square. So if you're looking at a hyperbolic orbit, where is the center of a hyperbolic orbit? Center.
The center of that,
Center of the hyperbolic orbit. Hyperbola.
there's no
That is the center. So this is M. This is C. This is F star.
That wouldn't be considered two different orbits. So you have one like this, and that's one orbit, and then another one.
So this is, so you have to understand, this orbit does not get occupied. Okay? So what you're seeing here is, this part of the orbit does not get occupied, but this is a hyperbola. Okay? Now what you have to understand is, what would be here? Give me an example what you would find here. Huh? Another planet, right? So if you're going from, let's say, you're going to Pluto, right? So what you're going to do is, you're going to,
Start at Earth.
this is, so you're going to go into, you're going to go outside of the Earth's orbit, right? And then you're going to use a planet in between Earth and
Pluto, in order to get there.
to slingshot. So this is that slingshot. Okay? It will just go and slingshot. So it will have, if this was a parabolic orbit, what would happen?
You want to have energy to make a slingshot?
Hmm?
With a parabolic order, you have energy to make a slingshot?
Right. It would try to slingshot and it would get stuck in the. It would have barely escaped the intermediate planet, but it doesn't have any energy left to go beyond. So it will be, the relative motion ceases. So here what is happening is, it has energy, positive energy to slingshot, escape this intermediate planet's gravitational pull, and still keep going. Got it? So you can do that multiple times. You can do one planet, another planet, another planet.
But only what
And it has to be, so you understand the planets are, you understand how the planes of the planets are in orbits? Have you guys seen?
no.
Have you guys seen demonstrations in the space museums and stuff like that? So only Pluto orbit is slightly, significantly out of plane, but all other orbits are relatively in plane, in the same plane. You see what I'm saying?
Doesn't Uranus rotate like a different way or something?
It rotates. Okay. Could be.
Like all the other planets rotate like this.
Uh-huh.
Uranus rotates like that or something.
Possible.
The other way.
I don't know. Yes.
I saw on the computer the other day that Mercury is in retrograde. So
Mercury is in retrograde.
was in
With respect to what?
Well, it was spinning. When they signed the article, it was like rotating backwards. No, it wasn't. No.
Instead of doing
It's not clockwise, it was like counterclockwise now.
But that, it depends, when you say retrograde orbit, you have to think about, is the sun rotating? Is the sun rotating?
No, you said rotates a little bit.
Right, so if your sun is rotating, it's slightly slowly rotating, right? So whatever direction sun is rotating, if Mercury is rotating in the opposite direction, or it's orbiting in the opposite direction, then it is a retrograde orbit. But if Mercury itself is rotating in some this way, something has to be launched into the Mercury orbit, and that orbit has to be the rotation, the direction of rotation has to be different with respect to the Moon. Then the orbit of that particular object or spacecraft would be retrograde. Alright. So if your Earth is rotating in this direction, right? So if you have most of the orbits we discuss are prograde orbits. You've noticed my orbits are always in this direction, going in counterclockwise, because Earth is also rotating counterclockwise when seen from the north. Okay. So if you go clockwise, that is a retrograde orbit. You have to look at the central body. So this is, what is this? This is the occupied focus. This is the unoccupied focus. This is the center. What is this?
RP.
This is for the
All things.
Huh?
This, no.
Is that
This is the center. So what is this distance?
Perigee.
Huh?
Perigee.
Where is the perigee?
It's from the pyramid, it's from there to the that's very
That's the perigee, right? So perigee is something.
Something minus something.
RP.
Huh?
Something minus.
So this is, what is this? What is semi-major axis?
A.
Huh?
A is
R8.
This is A. Negative A.
Go ahead, Tia, let's shut it down.
Oh. I'm like,
So center to perigee is generally the center to perigee is this A, right? So this distance plus this distance is the semi-major axis, right?
I thought A equals the semi.
A is the semi-major axis, but A is on the in the negative sense. Got it?
So
Yes.
perigee, that's one on the solar axis.
Perigee is the. So here, what is this? What is this?
That's cool.
That's the orbit. Okay. What is perigee? How do you define perigee?
Point of orbit closest to the closest being inhabited.
Right. It's the point of closest approach. Right. So if you look at point of closest approach to the central body, right? So this is the central body. The central body is at the foci or the focus, and this is the point, the closest point. That is the perigee.
So
R is simply, so here R doesn't change. How do you define the hyperbolic orbit? What is the characteristic definition of what is a defining characteristic? E is greater than 1 and
So it's
energy is greater than 0. Okay? So you have to keep in mind the table, the energy eccentricity table. For closed orbits, the eccentricity is either equal to 0 or between 0 and 1. The energy is negative. For parabolic orbits, the energy is 0, eccentricity is 1. And for hyperbolic orbits, the eccentricity is greater than 1 and the energy is greater than 0. So here you have these relationships still hold good. RA is equal to B square of mu. What do you see here? So this implies RA is equal to, huh? Right. Why is RA negative? E is greater than 1, right? So your RA is negative. Tell me what is RA there? Can anybody tell me what is RA? What is RA? Tell me, show me RA. What is RA?
It's a semi-major axis minus
Can you point it? Can you draw it? Can somebody draw it? Anybody wants to draw RA?
RA is known as,
Huh?
RA is known as the open.
Yeah, go ahead. Go ahead, Kiran.
Oh. I'm calling
Well, it's not going to be on the other side right there between C and S.
This is?
R, that's R. That's R, H is R.
That is RA.
Uh-huh.
So you see, RA is actually negative.
So it's for the center.
Because it's all the focus.
This is what is this?
RB.
RP.
From center to focus A.
This is
Negative A.
and this is
RB.
Why would they?
because it is in the opposite direction. It's going in the other direction. RA, what does RA stand for? RA is negative because of this. Okay. Why is RA? What does RA stand for?
A pair of any amplitude.
It's the radius. It's the distance. It's the farthest distance. RA is just like this is RP. It's the apogee radius or the apogee radius and perigee radius. So here another, this thing is b square over 2 minus mu over r is equal to mu over 2a. So this is very specific for hyperbolic orbit. You see this, what was this in terms of for parabolic orbit? V square over 2 minus mu over r was, what was it equal to? Total mechanical energy for the parabolic orbit? V V square over 2 minus mu over r was equal to?
The same.
Epsilon.
Epsilon.
Epsilon is what? For a parabolic orbit.
Oh, yeah.
That's the energy.
0, right?
Oh, it's
Okay.
So here it is positive. You see here it is positive. So the general term is, you see this is what we started with. If you remember, is epsilon, right? This is universal. Epsilon is equal to, is negative for closed, so it becomes v square minus 2, v square over 2 mu over r equal to minus mu over 2. We proved this because epsilon, see this proves that epsilon is negative. Okay? Epsilon is equal to 0 for parabolic orbit. So it becomes v square divided by 2 minus mu over r is equal to,
Papa, mu over 2a. Oh, you're talking about for that one. I don't know what that one. I'm sorry.
this is your discussion for energy. Okay. Now you see this is equal to mu over 2a because epsilon is greater than 0 for hyperbole.
So does that mean that energy is equal to mu over 2a, negative mu over 2a?
Yes, so we proved this. I did not prove it, but I told you guys this energy is equal to mu over minus mu over 2a. This statement says that energy is only a function of the size of the orbit. So I can say, I told you, I'll give you two expressions and say from that show that the size of the orbit or the energy of the orbit is only a function of size. A defines the size. So if you have, so what it means is, if this A, whether it is elliptical orbit, circular orbit, parabolic orbit, if they have the same A, can they have the same A?
Depends on
Let's say, think about a circular orbit and an elliptical orbit. Can we have the same A?
no.
They can have the same A. Why not?
I thought A depends on the shape.
No,
No,
A itself is,
E depends
epsilon is
Oh,
dependent on
okay.
size, not shape. Okay? They cannot have the same E, right? That we know. But they can have the same A. For example, this is a circle. So this is the ellipse. What is the listing for size of this?
from the center to the foci.
Center to the,
Foci.
not center to the foci. Center to, this is A, right? I can just take this and make it a circle, and these two orbits would be would have the same energy.
But why you have A's from foci to center on that?
Where is it foci center to?
It's to the orbit.
See here, what has happened here is, you see what is this distance?
That's the P, RP.
So this thing, if you see center
Okay.
is this plus this.
Yeah, it's the center.
It's this is this distance, and this distance is this distance. Correct? Yes.
So, like we did for parabolic orbit, we still have to find the hyperbolic orbit at the velocity, like how we calculated last parabolic orbit.
Parabolic orbit.
So, like, yeah, like with that equation there, like, yeah, that equation there, we don't have to solve the V, right? Or, like we did for the parabolic orbit last time.
Right. So you don't necessarily need to solve unless you're given A here. So here we're trying to prove something saying if you are in a circular orbit, if you increase the velocity of a circular orbit by 40%, by 41%, you will escape the gravitation. Okay, and that's what we were trying to do. Any questions?
This is midterm rotate.
This is all midterm material.
So it's.
Yeah, midterm. Let me make an announcement. Midterm is on. When do you want to? It
It's
is.
that Wednesday before break, so hold on.
That's the bill.
Oh, yep.
It's on the
About the bill, right?
5th is Wednesday.
Yep.
Okay. So 5th October will be your midterm. Okay.
In a study guide.
And whatever we cover until next Wednesday, that will be your syllabus.
The 28th.
28.
Okay.
I'll send you an assignment.
Can you start to your right, please?
Yes.
Oh, sorry.
I'll send you an assignment either today or tomorrow.
And it's gonna be due Wednesday.
Please give your attendance.
Yeah.
Sure. You need to talk to me. Yeah. How are you doing? Everything all right?
You doing alright?
Nothing good.
Okay, I'll go for you.
Okay.
I'll finish the rest of the stuff. You didn't do it. I do it.
Okay, and then after all these that,
Go sleep.
no, I gotta go here for some consultation. It's not, I'm not staying for more than an hour.
Okay, well, I'll tell
Well, yeah, I'll go, but you do it.
Jayla, you have to come to office.